this is really exciting to have a meeting with all these incline pool people, groundwater people. Thank you. So I just wanted to share some kind of a small paper that Sallie and I are putting together. We're about to submit. And it really is looking at this idea of using some sort of grazing incline pool critter, which here the dominant shrimp would be the Opaiula or Halocaridina rubra, to help us find sewage or see if sewage is in the groundwater ecosystems. In Hawaii, let's see, we have a number of groundwater-fed coastal ecosystems, which we've been learning about. But of course, they're found in all these other places. People from around the world are here, and you have your own. When we think of these systems, we have to remember that there is this sort of underground world where groundwater is flowing through porous bedrock, through incline pools, out to coral reefs quite often. And what can happen is if there is some pollution from septic systems or cesspools or broken infrastructure, we may actually get contaminants shown by orange here into the groundwater. So we know from a lot of work in all types of aquatic ecosystems from around the world that elevated nutrients can cause algal overgrowth, sedimentation as well. And there's lots of contaminants that are in there that may affect organismal health as well. So we want to avoid this pollution that's getting into these aquatic systems. Now, for quite a while, people have been using nitrogen isotopes as they move through the food webs as an indicator of sewage. And so some of you really know a lot about this and some may not. So I'm going to do a really brief introduction here, hopefully not too brief. But the basic idea is there are these dissolved nutrients in groundwater, ocean water, and the algae is going to uptake this dissolved nitrogen into its tissue. And these molecules and atoms are passed up to the grazers. So in this case, our Opaiula, our Halocaridina rubra. And we can measure nitrogen isotopes. Typically, it's measured as basically a ratio between nitrogen 15, which has one more neutron, and nitrogen 14. And so we typically look at this as, let's see. I'm not quite sure what that is. Okay. So we call this delta 15N, and it's in parts per thousand. Now, one of the cool things is there's been quite a bit of work in all sorts of systems telling us that we can expect these sorts of levels of N15 from these different sources. So atmospheric nitrogen tends to be 0, precipitation tends towards the negative side. Fertilizer, which is made from atmospheric nitrogen, has a very low value and a negative value at times. But sewage, you can see, has a very unique sort of signature. And this is because when the bacteria are chewing up the organic matter, the bacteria are releasing the lighter nitrogen, that nitrogen 14, and so the nitrogen 15 becomes concentrated. Now, one caveat here is if you have mixed sources, so if you have both fertilizer and sewage in a system, you may actually not detect it because they may sort of cancel each other out. But if you're getting a lot of sewage in a system, you're going to have really high nitrogen 15 values. So in our incline pool, here we have, it's not showing the whole screen, a little bit of it is blacked out. But we actually have some values for deep, high altitude or high elevation wells here in West Hawai, where Hunt measured 2 parts per thousand in this deep freshwater. Down here, the part of the screen that you can't see, the ocean water and deep saline water in wells are about 3 parts per thousand. So that's the signature in our dissolved water without any contamination. And therefore, we would see these values in algae, both in the ocean or in incline pools. And then this passes up the food web. Now, one thing you should know, and this has been studied quite a bit, is that as we pass up the food web, there's a bit of a concentration of N15 values, typically on the order of 2 to 4 parts per thousand. So that's what we expect in our uncontaminated areas here in West Hawaii. But if we've got sewage, we're going to bump up those values above what is expected, and we would expect to see higher values. Now, why are we even talking about using a grazer for N15 when we could be using algae? Well, one of the things that we have been hearing is that, first of all, water is a potential source, and actually a lot of our monitoring, we look at water quality, but water is zipping through some of these pools in sometimes less than an hour. So if you measure the water levels of nitrogen, you may be missing pulses. The other thing that's going to happen is a lot of the pools here don't have any macroalgae. They don't have limit to collect. And so you're sort of going to have that. Now it's there, it's just microscopic. But what we do have are these grazers. And so the grazers are busy, they're eating the biofilm, they're taking up the algae. There's been a lot of work from folks in this room, from Hairston's lab at Cornell, from Barbara Seidel, from Troy. A lot of people have looked using stable isotopes for food webs in these incline pools, but not just necessarily looking for sewage. So Sallie and I did a small project looking at what are the spatial patterns of nitrogen-15 in the shrimp tissue. What is the relationship between the tissue nitrogen-15 and water quality parameters that are collected on a regular basis from the inventory monitoring program? And we also did a small Mesocosm experiment, which I think I'll have time to show you some results. So here we have West Hawaii. With the black are a number of pools that I had collected stable isotope data in back in 2014 when I was at UC Berkeley. The red are actually a map of all the on-site disposal systems for sewage. This is septic tanks and cesspools. You can see there are some along the coast, especially up near Puako. The highest density is down near Kona. The other thing to note is this orange, or that's yellow, triangle is the Kealakekee wastewater disposal basin, where our water treatment center here in Kona actually disposes partially treated wastewater. And there have been a number of studies looking at how that water gets out offshore into the ocean and the corals. This is Kaloko-Honokōhau National Park, which we've been hearing a lot about. So between in 2016 and 2017, we went ahead and each of these pools, this is the national park boundary, each of these pools was a site that we collected 10 shrimp for nitrogen-15 tissue samples. And we also collected 3 water quality samples with the inventory monitoring protocols and analyzed those. We have, these are the colors you'll see, or you're going to see in future graphs. But the north portion is orange, then we have the central portion, a portion just north of the harbor, and then, which is called south, the south part of the park. And then we have an area south of the harbor. So what do we find? Well, this is from the tissues of the shrimp, and you see of individual shrimp, and so you see here's our N15 values. Here we have individual pools, and you can see clusters of these different areas in the park. The pools in each cluster are very close to each other. You also notice that of the 10 shrimp, there's actually not a lot of variability in each pool, which is a good sign if you're going to use this for a bioindicator. And then finally, you see, whoa, look at this, way up in the 20s. That's a really high value. So there's definitely sewage going through these pools. There might be a little bit in this is the south area of the park. How does this relate to the dissolved nitrogen, phosphorus, and other things that we're collecting in the water? Well, you can't see the x-axis here, but this is total dissolved phosphorus. And then here we have nitrogen-15 on this axis. And you can see there's a very tight relationship, a significant positive relationship. Again, here's our really high values for sewage and N15 and high values of phosphorus. And year to year, this was the same in both years. How about nitrogen? This is total dissolved nitrogen. And you can see what's interesting here is the 2 years differ. And if you were to go out and just take this measurement, you might think, oh, okay, nitrogen's lower in these pools, but this measurement is much higher. However, the actual shrimp tissues are the same. So one value of using tissue samples is they have more of a time-integrated signal of sewage. And so if you have pulses of phosphorus or nitrogen coming through a system, you might actually miss them. So now we can talk a little bit about the Mesocosm study. I can talk a lot more about this with folks if you want, but Sallie, Kailua helped me with this. And basically, we took shrimp and put them in these containers with water from this pool, 84, right down here near the harbor. And every week we would give them fresh substrate that had been incubated in these pools. The control group got food from the same place, and our sewage group actually got their diet shifted on them. They got some stuff from these pools that had a high sewage signal. And as we expected, the control group, over 77 days, we collected shrimp every week, their tissue signals didn't change that much, right? They're getting the same food, so they were clicking along, and this is an average of 3 shrimp a week. And then our shrimp that got lucky and got that high nutrient diet, right, their nitrogen 15 values took off. And I can show you the model, but basically we're seeing about a 20-day turnover for about 50% of their tissue turnover for nitrogen. So what this is telling us is that the shrimp are time integrated and that they are shifting to this nitrogen 15. We're not imagining things, that their tissues are based on their diet. This has been shown in many, many studies, not just this. So to wrap it up, I think that this poses an opportunity potentially that using some sort of grazer, especially if you work in cave systems and you don't have macroalgae or limu, this might be a really possible way to sort of help you detect if there's sewage or not. As time integrated, it's a relatively affordable way to look for sewage pollution. If you use caffeine or over-the-counter drugs, those are a lot more expensive samples to run. And ideally, you're detecting pollution also before it gets to the coral reef. So we had particular help with Kailua and Amanda, and Farahi helped. So I really want to thank you all for this, and I just really appreciate everyone here who's working so hard to protect alkaline pool and groundwater systems. So thank you.